Okay. Wonderful. Welcome, good evening. Welcome to another interesting talk in the frame of the module Emerging Fields in Architecture. Today we have a very interesting talk about building in Antarctica and other extreme environments by Hugh Broughton from Hugh Broughton Architects. Hugh Broughton founded Hugh Broughton Architects in 1995. The practice is based in West London. And in 2005, Hugh's practice won the international competition for the design of this Antarctic research station, Halley VI. It's a modular elevated base that was completed in 2012 and is still the world's first fully reloadable polar research facility and the best known facility and one of its kind. Still in 2023, but Hugh's practice has gone on to win a string of design competitions for other remote projects, and the practice is now considered one of the world's leading designers of research facilities in polar regions. His projects include, of course, the Halley VI Antarctic station, but also a Spanish Antarctic base that is called Juan Carlos I, the Atmospheric Watch Observatory in Greenland for the US National Science Foundation, the Scott Base redevelopment for Antarctica in New Zealand, and an Antarctic infrastructure renewal program for the Australian Antarctic Division. Overall, until today, Hugh has won over 50 international awards for his designs, and his work has been published around the world. And of course, he has exhibited his projects and talked on television and radio. He has lectured worldwide on his work of his practice, and I'm very glad that Hugh Broughton found the time to tell us at the TU Vienna in the module Emerging Fields in Architecture a little bit of his work and his approach and his success story. Thank you, Hugh. Welcome again, and the floor is yours.
Thank you so much, Sandra, and thank you so much for inviting me to talk to you all. It's always a real pleasure to talk to the students in Vienna in this way, so thank you so much. I'm just going to share my screen. There we go. So, welcome everybody. I'm going to talk today about my experiences building projects in Antarctica. So you please do put any questions you might have into the chat room as I'm going along, and I'll look forward to a really good discussion at the end of the presentation. So I don't know how much you know about Antarctica. You obviously now all know a lot about space, but Antarctica is a continent. It is actually, of course, the coldest, but also the windiest and the driest continent on Earth. In the summer, it's the smallest continent on the planet, but in the winter, when the sea freezes for up to 300 to 400 kilometers out from the coast, it grows to the fourth largest continent on the planet, roughly the size of the USA and Mexico joined together, so sizable. But it has only a population of around 2,000 people in the middle of the winter. And if you took the population density of Antarctica and then applied that, for example, to my country, the United Kingdom, there would only be 13 British people in the world, which some people might think would be a good thing. My own experience working in Antarctica has become quite extensive. As Sandra mentioned, in 2005, we won a competition for the design of the Halley research station. But since then, we've been involved in other designs for the British Antarctic Survey, also for Spain, for Australia, for New Zealand, and for the US. And today I'm going to focus on showing you the designs for Halley and for Scott Base. But I'm going to then finish by just showing you a project which we did last year with two artists, considering how we could apply lessons learned from Antarctica to the design of projects in space. So let's start with Halley. So Halley is on the coast at 75 degrees south. That means it's around 1,000 kilometers from Halley to the South Pole. It's an extremely cold, windy, and exposed site. It's located on an ice shelf. So an ice shelf is where you get the ice flowing off the main continent of Antarctica and then continuing to flow out over the sea, so that the ice is actually supported by sea underneath rather than by ground. And the ice shelf on which Halley is located, the Brunt Ice Shelf, is 150 meters thick, and it's moving all the time, flowing out to sea, a bit like water, at a rate of 400 meters per annum. So this means it's a very dynamic site, constantly moving and changing position. It's extremely cold at Halley. In the summer, the temperatures might be -5, -6, but in winter, the temperatures can go down to -50, -55 degrees Celsius. It's also extremely windy because it experiences wind, cold air, which drops off the plateau at around the South Pole and descends down towards the sea, creates winds called katabatic winds, which blow in excess of 150 to 200 kilometers per hour at the site of Halley. And at those wind speeds, the wind picks up all the snow and ice that it encounters along the way and creates massive drifts around anything that is left on the snow surface. So snowmobiles, cargo, containers, everything will get buried, including big buildings if they are left on the ice surface. So as a result, the previous station to the one we designed, Halley V, which you can see in this photo here, was elevated above the ice surface so that the wind could blow underneath, reducing the amount of snowdrift that develops around the buildings. And every year, the building had to be jacked up above the rising ice and snow level to keep it free from snowdrift. And that's what you can see in this photo here, is all the people on the station helping to jack the building above the rising snow level to keep it free from snow. In winter, it is dark for around 105 days per annum. So that's quite an extreme environment in which to live in. No daylight, no sunlight, total darkness for more than 3 months. The interiors of the previous station, Halley V, looked like this. So they were old-fashioned, very institutional, quite lonely spaces with this central corridor. And the way the building was arranged was every activity had its own room, a dining room or a bar or a room for watching the television. And so people would be walking up and down the corridor and they'd hear people laughing in the bar. And some people, that would be, oh, that's good, I'll go and join in where the fun is taking place. But other people felt socially challenged by hearing the laughter, and so would just carry on walking past the bar. And they would develop what was called the Halley stare, whereby they would just constantly just be staring forward, walking up and down the corridor, building up their courage to join the other members of the community behind all those doors off the corridor. So yeah, quite a difficult environment for some people to live in. There's the benefit, however, that in the winter, when the sun does eventually rise above the horizon, that you can go on amazing trips to go and visit your neighbors. And here you see two British Antarctic scientists abseiling down the cliff at the edge of the ice shelf onto the frozen sea to go and visit a colony of emperor penguins that lived close by. So an amazing experience. Everything that is needed to keep these research stations functioning properly has to be delivered by plane or by ship. And in fact, anything of any large scale definitely has to come by ship. And the ship comes in the summer season when the sea ice has melted close to the edge of the ice shelf. And everything is then unloaded from the ship onto the sea ice and then dragged across the sea ice to the edge of the ice shelf, where the British Antarctic Survey used bulldozers to create ramps so that they can then drag it up onto the ice shelf and then across to Halley, which is maybe 10 kilometers, 15 kilometers further inland. And the sea ice is frozen maybe 2 meters thick. So everything which is delivered has to be within a maximum weight of 9 tons to prevent it from breaking through the sea ice. By plane, some things can be delivered, but only very, very small objects, because the only planes that can fly to Halley are these twin otters, which you see in this photo here, which are excellent for landing on the ice, but very poor for carrying cargo. So, for example, there were just 5 of us in this plane when we flew to Halley, and it has to refuel on the way, landing at remote refueling depots where the British Antarctic Survey have left fuel in oil drums for refueling the planes as they fly through from one station to another. So you might wonder, it's so dark, it's so cold, it's so windy, and it's so isolated. Why would anybody want to live and work at a place like Halley? And the answer is pretty simple. It's because the science that is conducted at these research stations is of global significance. So, for example, it was in the mid-1980s that 3 British scientists working at Halley first discovered the hole in the ozone layer. And this discovery then led to the Montreal Protocol banning the use of CFCs, which still remains to this day one of the most important pieces of global environmental legislation. But it's not just the hole in the ozone layer. There are incredible research taking place into the interaction between the sun and the Earth's atmosphere, into changes in sea temperature, changes in the wildlife that lives in Antarctica, and also the melting of the ice caps that then drives sea level rise and changes weather patterns all around the world. So this is science of truly global significance, which is why so many countries have research stations in Antarctica. However, around 25 years ago, the British Antarctic Survey noticed a problem in the Brunt ice shelf. They saw that the site of Halley V was on the wrong side of a potential crack line in the Brunt ice shelf that would see everything to the left-hand side of this map disappearing as a giant iceberg. But of course, Halley V was designed on legs that were frozen into the ice, so could not easily be moved. So they realized they were going to need a new station, Halley VI, to replace Halley V, and then they would need to remove Halley V from Antarctica before the iceberg broke off from the Brunt ice shelf. So to do that, they decided to hold an international design competition to come up with new ideas for the design of research stations in Antarctica. They had 86 entries from around the world. They shortlisted 6 teams to develop initial designs, then chose 3 to develop their designs, and then finally chose our team and the engineers ACOM as the winners. But just before I show you the designs and the finished building, let me tell you a little bit about the history of buildings at Halley. So the first station at Halley was constructed in 1957, which was the International Geophysical Year. And it was a very simple building, a timber hut with a pitched roof that was built onto the ice shelf. And then year on year, as it snowed and the wind was blown around this area of Antarctica, so the snow level rose by around 1.5 meters per annum. And eventually the building became totally buried. When they were constructing, when the building got buried, eventually the snow came right the way up to the top of the roof, and then they built tunnels or shafts to climb down ladders into the building. But eventually it became crushed by the ice. And so here you can see some of the early examples of, just go back one. Here you can see an early example of Halley's 3 and 4 before they became totally buried. These buildings were designed after the experience of Halley 1 and Halley 2 to be specifically be buried. So they were designed as tubular structures, and you can see here the shafts with ladders that were placed in them so that as the snow level rose, the buildings became buried and people could climb down into them. But it was a very unpleasant way to live. You can just imagine, not only is there now darkness in winter, but there's also darkness in the summer as well, because you're under the ice. And all the time you can hear the ice moving around you, creaking as it starts to crush the buildings. You had the generators making the power were in the buildings, so the whole place smelt of diesel fuel. And also you have the sewage treatment plant, so the whole place smelt also of sewage, smelt of sewage, of diesel, and of food. It was a very, very unpleasant environment in which to live. And unsurprisingly, these buildings only lasted for sort of 8 or 9 years before they had to be replaced. Looking around Antarctica at some of the other buildings that people had been building at the same time, one of the greatest examples of innovative design was probably the South Pole Station, built in 1975 by the US. And this was designed by Buckminster Fuller as a geodesic dome into which accommodation was then placed to protect it from the wind and the drifting snow. And you can see on the top right, the accommodation placed inside the dome. But this building also became buried and damaged by the moving snow and ice and was subsequently replaced. And here you can see some of the newer generation of Antarctic research stations. So on the top left-hand side is the French-Italian base called Concordia. On the top right is the US base at South Pole, the Scott Amundsen base. The bottom left is the German station, Neumayer 3, and the bottom right is the Belgian station, Princess Elizabeth. And all these buildings you can see are now built raised above the snow and ice to allow the wind to pass underneath, removing snowdrift, making them more pleasant in places to live with views out onto the landscape around. All aerodynamic shaped buildings, and all with different methods in which to keep climbing above the snow and ice. So electric screw jacks at the South Pole, hydraulics at the French, Italian and German bases, or just built on rock and elevated above at the Belgian station. However, at Halley, we had different challenges, because not only did we need the building to be lifted above the snow and ice so the wind could blow through to remove the snowdrifts, we also needed the buildings to be relocatable so they could be moved from one place to another to escape the fate of Halley V, which was going to disappear on an iceberg. So if the buildings are mobile, you can move them to a new place, and then you can escape the risk of the site breaking off as the iceberg. So we came up with this idea of modular buildings, a repeating module, elevated on legs and then supported on giant skis. And here you can see the developing concepts for these modules. So each one is around 150 square meters in area. It weighs between 60 and 80 tons, depending on the function. It's raised 4 meters from the snow to the underside of the module on hydraulic legs on giant skis. And the hydraulic legs allow the legs to retract inside themselves, so you can push snow underneath and then jack them up above the snow that has risen all around you. And the modules are used for bedrooms, for laboratories, for offices, and also as energy centers containing power generation, fire suppression, water production, sewage treatment, etc. But whilst we developed the blue module of 150 square meters for most of the functions, we needed a special module to accommodate the social functions of the station, the dining space, recreational areas, places to watch TV, places to access the internet, and so on. So for that, we developed this larger 350 square meter module, which was arranged on 2 floors and had the noisier activities on the lower level and quieter activities on the upper level, and then linked by a nice helical stair. When we first entered the competition for Halley, we came up with the idea of a climbing wall as well for going between one floor and another, because all the people who work at Halley are very interested in outdoor activities. But then the British Antarctic Survey Health and Safety Officer noticed that we had a climbing wall and a bar very close together and thought that would be too dangerous. So said, you've got to make a choice between one and the other. So unfortunately, the climbing wall disappeared out of the design. So how did we build this design? Well, one of the keys to designing in extreme and remote environments is to do everything once in a safe, warm and temperate place, so that when you do it the second time in the cold and extreme place, you know exactly what you're doing and less things can go wrong. So for Halley, we built test modules in South Africa, where the steel and the cladding were manufactured. And we tested the operation of the hydraulics, the air tightness of the modules, the rigidity of the steel frames, so that we knew that everything would fit together and function as expected. And here you can see some photos of those test modules against the backdrop of Table Mountain or the suburbs of Cape Town. And then when we were happy that everything was working perfectly, everything that was required to build the station was loaded onto this ice-strengthened cargo vessel and then shipped to Antarctica, where the largest component, which is the steel substructure of one of the standard modules, was unloaded onto the ice and then pulled up to the ice shelf and then off to the site of Halley VI. And on arrival at the site of Halley VI, what comes is this steel space frame on the top left-hand side, which is then has the hydraulic legs installed, allowing it to be lifted up. And then they put prefabricated floors on top. And then bottom left, you can see one of the energy modules with the generators, fuel storage and switch rooms and so on being installed. And then here you see the steel frame being installed over the top of that. And here you see the cladding being installed onto the steel frame. And the cladding is made of glass fiber with a high level of insulation inside to make it thermally very efficient. And we use glass fiber panels because they work very well in low temperatures, but also they could be very well insulated, and also very large panels could be made. So this panel here, for example, is about 12 meters long by about 3.5 meters high and has already got all the windows in, all the finishes and so on. So the buildings could be fully clad and made airtight very quickly. And all the cladding and the building services and a lot of the interior elements were constructed and installed at the site of Halley V, which was used essentially like a hotel for the construction workers. and the whole process of construction was done like an assembly line, like you get in a car factory. So one team doing the building services, one team doing the steel frame, one team doing the cladding, and then a special team working on the big red central module. And then when the modules were fully clad and had most of their interiors installed, they were lowered down on their hydraulics onto the skis and then pulled 15 kilometers inland to the site of that Halley VI was going to be deployed, so that they could be joined together. And here you can see two of the blue modules being joined together. One on the left has just arrived, has been pulled by the tractor that you see underneath. Then it will lift itself up using its hydraulic legs and be connected together using these flexible connectors like you get between train carriages. And here you can see all the modules joined together, ready for Halley to be operational through a winter season. And on the left-hand side here, this is a science module with an observatory for looking at the weather and measuring ozone on the top. Another science module with a deck with instruments on top. Then two energy modules for power generation, water treatment, sewage treatment, fire suppression, and so on. The main two-story social module with the dining, the bar, the TV watching, and the gym in. The command module, which has got communications, the doctor's surgery, the base commander is located here. And then two modules for sleeping, each with 8 bedrooms with bunk beds. So you can have 16 people sleeping in each module, 32 in total on the station, with also bathrooms and a quiet lounge for people to escape from the bigger community of the station. And it's split in half by this bridge link, which allows sharing of power and water, but separation so that if there is a fire in one side, you can escape to the other and live there until you can be rescued, which may be many, many months after the fire, especially if it takes place in the winter. So this is the south end of the station with the 2 science modules and the energy module. And this is the inside of the science observatory. And the man at the end there is using a Dobson spectrophotometer for taking measurements of the ozone layer, continuing a tradition which has taken place at Halley for decades and which is helping to chart both the development of the hole in the ozone layer and its subsequent but slow recovery. Moving down the line of the modules, this is the main social module on 2 floors, and this big window here uses a combination of clear glass, which are the black triangles, and then glass which is insulated with a material called aerogel, which gives it amazing thermal performance but allows lots of natural light through. And this material was invented by NASA to insulate the ends of the space shuttle for re-entry into the Earth's atmosphere. So amazing insulation properties. And here you can see the effect internally within that double height space, which is where the pool table is placed. And the big triangles is actually clear glass looking out onto the ice. And the smaller diamond shaped windows are actually this white translucent aerogel insulated glass, but letting through lots of natural light. This is the stair leading up to the upper level of the central module. And like all good British buildings, it had a picture of our monarch, at that stage our queen, but the picture has obviously now been replaced. The stair is surrounded by timber panels, which are finished with Lebanese cedar, which is a timber which gives off a really nice smell. So as well as thinking about ways that we could address the darkness and the extreme cold weather, we also thought of all the deprivations that people experience in extreme environments, like smell of natural phenomena like trees, and tried to introduce those into the project to help people's general health and well-being. This is the upper level of that central module, which has a big oval and domed window that you can stand in to admire the Aurora Australis, which is the southern lights, like the equivalent of the northern lights you see in Norway, without having to go outside. As you get to the north end of the station, you get to the 2 modules which contain the bedrooms. There's also a doctor's surgery where they can carry out medical operations. We worked very closely with a color psychologist who developed a special palette of colors to help people overcome the effects of winter blues or seasonal affective disorder. The circulation areas at the heart of the modules have a higher ceiling to allow natural light through roof lights. We used a vacuum drainage system within the buildings because that essentially sucks the waste out of the toilet or the wash hand basin and uses far less water, 1 litre to flush the toilet instead of 7 or 8 litres in a standard toilet. So really cutting down water use, because otherwise all the water use has to be made by melting snow and ice, which uses a lot of energy. This is one of the bunk bedrooms. So they're quite small, quite compact, but at the same time quite comfortable, with lots of storage and lots of other special features, like a special light that is just in the corner over here, which simulates daylight and acts as an alarm clock to wake you up in the mornings in the winter, with this artificial dawn helping to balance your serotonin and melatonin and overcome the effects of seasonal affective disorder. There's also things like a fold down mirror within the work surface here that you can flip up to help you do things like your makeup. So here you see the station from the air. You can see the effect of elevating the building. The wind blows from the left-hand side underneath the buildings, and then drifts are formed on the leeward side of the buildings. And this is the view of the station from one end after all the snow has been leveled and the building has been jacked up, ready for another winter. And here the view of the building in the middle of the winter. So the wind is blowing from the left-hand side. It blows underneath the buildings, scouring away any snow from the skis, and then creates a drift on the leeward side. So the skis are kept free from the snow and ice so that they can be lifted up to account for changes in level and when you need to jack the whole building above the rising snow level. And here's a view of the building at the end of winter, covered in a thin layer of ice. And what this photo also shows is that the insulation works really well, because the only place that the ice has melted is where the windows are. And here a view of the station at the time of the Queen's Diamond Jubilee. And you can see the most southerly people, southerly British people, actually playing cricket underneath the module at -40 degrees Celsius in a 70 km/h wind. The station is used by the British government as a demonstration of innovation. It's also appeared on stamps and even on a coin, but unfortunately a coin that you can only spend in the British Antarctic territory. So not too many places to spend your money in that place. And then most amazingly, this is the greatest accolade for any architect. Somebody actually had a tattoo of the building cut into their arm, which I think, just shows the privileged position that they feel that the building should have. So for us, the most important thing, however, is having completed Halley, is that we were able to work on a number of other research stations. The first one we worked on was the Spanish, Juan Carlos, on Livingston Island. And this is a picture of Livingston Island before our development took place. It's used only in the summer, but it has a big challenge. In the summer, the snow all melts, and in the winter, they get very high snowfall, up to 3 meters of snowfall, and the buildings all get buried. So we had to design to take account of that change in the snow level. There's also a lot of wildlife that lives around the site of the Spanish station, including leopard seals, gentoo penguins, elephant seals, and also a lot of very rare mosses, which are most unusual in Antarctica, where only 2% of the continent is free from ice. The seals get absolutely everywhere. They come into the buildings if you leave the door open. They lie on the fuel pipes. They will get under the vehicle tracks everywhere. The other unusual thing about the Spanish station is that there are also neighbors. The Bulgarian station is only around 4 or 5 kilometers away, although you can only reach it by boat. And here you can see a picture of my visit to the Bulgarian station and the great hospitality that the Bulgarians offered with these nice bottles of raki that made the journey feel much warmer than I had anticipated. And here is our design for the Spanish station. Again, a repetitive structural design, buildings elevated just off the snow level to allow the meltwater to flow underneath, but with a lower level. So in summer, you can, when all the snow melts, you can go through the door, but with an upper level so that you can go up this stair to get into the building at the start of the summer season, when the snow level can be right up to this sort of 3-meter zone just here. And split between the main habitat, which is 3 buildings joined with a central core, and the science building. So if there's a failure in the habitat, people can escape to the science building until they can be rescued. But because the wind blows from every single direction, the buildings didn't have to be oriented in any particular way to respond to the wind, because it just blows from every direction. And here you can see the finished building, which was opened around 2 years ago. The next station I was going to show you is at Scott Base, which is the New Zealand station, which we're currently designing and which starts in construction in September this year. So this is the current Scott Base, which is on Ross Island, which is an island off the coast of Antarctica, and which also has this incredible volcano on it called Mount Erebus. Ross Island is a very historic site because it's where all the great explorers sailed to before setting out to try to reach the South Pole. The New Zealand government has operated a research station on Ross Island since 1957. The station was established by Sir Edmund Hillary, who was famously the first person with Sherpa tensing to climb to the top of Mount Everest. And Hillary had the building of the first Scott Base made in New Zealand and then shipped as modules, flat pack modules, to Antarctica. And in just 1 year, he had designed it, fabricated it, and erected it in Antarctica. And here you can see the original base, a series of buildings connected together with a tunnel. And then in the 1980s, the base began to be redeveloped with new buildings replacing the smaller modules, so that now only one of the original modules survives, but which has been beautifully restored by the New Zealand Antarctic Heritage Trust to exactly match how it was in 1957, when it was first completed by Sir Edmund Hillary. These are some of the other historic structures in the nearby area on Ross Island. This is Captain Scott's Discovery Hut, which he actually purchased from a builder's merchant in Australia, which is why it has this veranda round the outside, because it was made for a very hot climate. Unsurprisingly, it had no insulation and was a truly horrific building in which to live. So cold that in fact the crew mostly stayed on the ship, the Discovery, and used this building only for storage. Also close by is Sir Ernest Shackleton's hut at Cape Royds, which is a much more pleasant construction with cork insulation, which made it much warmer to live in and had a fireplace in it, and was really a much happier environment for the expeditioners to live in. Close to Scott Base, there's an American station called McMurdo, which is the largest station in Antarctica, which has a population of 200 in winter and up to 1,000 people in the summer. And it's like a small mining town or oil field research space in Alaska. But at Scott Base, although redeveloped in the 1980s, many of the buildings have developed serious problems. It's on multiple levels, which makes it hard moving equipment from one end to the other. The services are contained in very tight spaces, which are difficult to maintain. Much of the key equipment is very old, in particular the water production plant. The fire safety is compromised in numerous locations, and you can see here, you have to open this door and then climb down this ladder to get to the ground in case of fire, which is dangerous. Snow drifting occurs all over and has to be very carefully managed. And in fact, people even have to climb onto the roof to remove snow, which is obviously very dangerous. So in 2017, we began working with Antarctica, New Zealand to develop ideas for a new research facility. And these are some of the early sketches investigating the idea of elevated, interconnected modules or buildings arranged parallel to each other, but connected by bridge links. We came up after a lot of analysis, we settled on the principle of buildings raised up parallel to each other, but connected by bridges. And then we tested these in a water flume at the laboratories of RWDI in Canada. And so the way that works is they have this tank of water. You make a model of, first of all, the existing station. You put that into the water tank, and then you introduce a current in the water, and then introduce sand into the current, and the sand flows in the water over the buildings like snow being blown on the wind, and then drifts out around the buildings in the same way that snow would drift around. And in that way, you can see what works well and what doesn't well. We put the existing base in first, so we can calibrate the model, and then our proposals. And as we see, some things work better than others, so we were able to refine and change the design to get to the optimum solution, which minimizes snowdrift to the absolute minimum. And in that way, our design changes the existing base from this to this, with 3 parallel buildings, 25 meters wide, each made up of 6-meter sections. So this building here is around 84 meters long, the same one here, and this one is about 60 meters long. The top building contains the bedrooms, the dining space, the other social spaces, movie room, library, and so on. The middle building contains offices, but also science laboratories, collaborative workspaces, places to get ready to go and do science in the deep field. And the bottom one contains stores and workshops. There are also 2 helipads and areas for collecting together cargo before going out into the field. And here you can see the station on the slope of Pram Point, which is this part of Ross Island here, surrounded by frozen sea. Here is Observation Hill, where Captain Scott's crew used to go to the top every day to look to see if they could see him returning from the South Pole. And then when he never did return, they built a cross in his memory on the top of this hill. McMurdo Station is just on the other side over here. A really interesting part of the project has been integrating Maori cultural design into our design for the Antarctic setting. And as part of developing our design, we spent time with the Maori community in Christchurch, understanding their respect, I suppose, for environment and landscape, and looking at ways in which we could integrate that into our design. So here you see the design team all collected together, having spent the night at a Maori meeting hall or a marae. We were also very conscious of the history of New Zealand's Antarctic expeditions, particularly of Sir Edmund Hillary's expedition of 1957, and admired the way in which colour was introduced by the architects of these buildings, Sir Frank Ponder and looked at ways in which we could repeat that concept of introducing colour into the building design. Here you can see the current design. So this is the entrance to the main accommodation building, which has a big deck outside for people to get together and good views into the building as well, giving a strong sense of welcome, which again was a key feature that came out of our discussions with the Maori community, creating buildings where you could give a proper welcome to visitors. This main building is arranged with a double height space in the middle, you can see here, with permanent or longer term bedrooms looking out onto the landscape, and short-term visitors in bedrooms which look into the double height space. And then on the lower level, we have things like food storage and also the plant rooms with all the building services in, with this walkway running along the full length so that you can access all the pipeworks for maintenance. The buildings are elevated above the ground so that the wind can blow underneath, with this aerodynamic shape on the wind side to channel the wind underneath, and then curved geometries to guide the air over the top of the buildings to again help drive the snow as far away from the buildings as possible. I mentioned colour for Halley, and we have worked with the same colour psychologist, Angela Wright, in the design of Scott Base, but with a different palette of colours to reflect the interests of the community who are going to live there, much more in tune with natural colours of New Zealand and how those could be reflected in the design of the base. And here you can see how we've applied those to some of the interior features. So this is the entrance hall with the potential for a display of the history of expeditions in Antarctica, but also talking about the science that the scientists from Antarctica, New Zealand carry out. A briefing room using timbers from New Zealand to create a warm, welcoming environment. The double height space, again, using timbers from New Zealand, but with the display of all the people who've spent time at Scott Base through the winters. A bar, again, with good views out towards the black and white island, which lie to the south of the station. Everyone who stays long-term at the base gets their own bedroom with a desk, a view out, lots of storage. And here's the library at the far end of the main accommodation building, again with comfy spaces to sit in the window and admire the views, or sit and read a book, or just talk to one or two other people. The buildings are connected with bridge links, with panels running all the way under the windows, so you can access the building services to maintain the building as quickly and easily as possible, because maintenance and the ease with which you can access services is a key part of living efficiently in these extreme environments. There are windows in the bridge links, so you can look out onto the natural environment round and about, helping to orientate yourself. And then as you move into the main office and science block, there's collaborative workspace where people can share ideas, but also look in and see people working in the laboratories. And then downstairs, it becomes more industrial, with areas to bring together everything you might need before going out on an expedition deep into the Antarctic countryside to go and research whatever it is, glaciology, sea levels, biology, and so on. So as I mentioned, there's 3 buildings. Building A is for accommodation, Building B is for science and administration, and Building C is for the workshops and the stores. And here you can see the vehicle workshop in Building C. So it's quite a varied collection of spaces, from bedrooms to libraries to dining space to bars to movie rooms, medical facilities, through to offices and science labs and expedition arrangement spaces, and then through to heavy workshops for maintaining the vehicles which are needed to get people out into the field. The new base, the current base is partially powered by diesel generators and partially by 3 1-megawatt wind turbines, but the new base will have the wind farm doubled in size to 2 megawatts, which means that generally 70% of the energy demand for Scott Base will be met by renewable energy sources. And on a really good day, when the wind is blowing well, 98% of the energy will be renewable energy from the wind farm, which is a dramatic change from the historic Antarctic stations, which rely entirely on diesel power generation. To construct the new Scott Base, we're going to make it in New Zealand, build it entirely in a port in the South Island of New Zealand called Timaru. And then when the building is completed, it will be basically cut up into 8 sections and loaded into a flat-based roll-on, roll-off ship, and then sailed to Antarctica and then unloaded using the self-propelled motorized transporters, which will take it into position so that the sections can then all be joined back up together again to create the new Scott Base. And the benefit of this is that all the construction really takes place in New Zealand, where it's warmer, and only the final elements of construction are done in Antarctica. So you reduce the number of people who have to travel to Antarctica, you reduce the amount of transportation, and therefore the environmental impact on this otherwise pristine continent. And here you can see what the construction site will look like. So the existing base in the foreground here will be retained as the accommodation for the construction crew. And then the new base will be built on the hillside behind the existing base. And when the new base is complete, the existing base can be demolished. And at that point, this will be the view of the base with the 3 buildings essentially stepping down the hillside of Pram Point, joined together with bridge links, with the aerodynamic shape of the building facing into the prevailing wind to allow the wind to blow underneath the buildings, keeping them free of snowdrift, and then all powered by wind power that you can see up on Crater Hill above the station. And just before I finish, I thought I would show you how we have applied some of the lessons that we've learned in Antarctica to a theoretical project for space, but a theoretical project which we actually built. And if you think about Antarctica and space, they're not too dissimilar. Everything that you need to transport to Antarctica has to be delivered in the restrictions of shipping or aeroplanes or rockets if you're going to space. It's an extreme environment where it's really difficult working outdoors. You can only work for very short periods. You have to wear very restrictive clothing whilst you're carrying out the construction. And therefore modular solutions like we see in space or Antarctica are really going to be the best way of making any building. The project which we have just carried out is this project was envisaged by 2 artists called Ella Good and Nikki Pierce, who were 2 artists who came up with the idea of building a Martian house. And the idea was to build a prototype house in Bristol in the south of England, which would act both as an experiment of what it would be like to live on Mars, but also as a way to look back on our life on Earth. So we would have to think very carefully about the resources we used, the food we ate, the things we needed for our survival. And in that way, it helped us to think hard about minimizing water usage, growing plants using hydroponics, recycling water, living in small spaces. So we came up with this idea on Mars. Obviously, there are other challenges different to Antarctica, in particular, the challenge of radiation, both cosmic and solar radiation. one of the things we discovered through working with two scientists at the University of Bristol was that under the surface of Mars, there are lots of tubes caused by volcanoes, which are lined with lava, and that these tubes could be utilized for accommodation to protect people from cosmic and solar radiation. And therefore we could place some accommodation under the ground and then just have the living spaces above ground so that they could have a view out, learning from the lessons of those underground buildings that were once used in the Antarctic. But of course, if you build above ground, you still have to protect yourself from cosmic and solar radiation. But you need to be able to transport your buildings very efficiently, because obviously everything has to be brought in a rocket from Earth. So our idea was to create accommodation out of inflatable structures, but instead of filling the inflatable structure with air, we fill it with regolith and the frozen water that you get on Mars, creating a homemade concrete. So essentially the inflatable structure is a formwork for this homemade concrete to then protect you from the radiation. And the windows would be triple glazed windows with the layers between filled with water that then reduces the energy, solar energy getting into the building, but also protects you again from solar and cosmic radiation. And that's what you can see on this upper level here. So with sleeping accommodation, plant space, a small kitchenette on the lower level, and then living space on the upper level. And this was our proposal for siting this prototype house in Bristol next to the M-Shed Museum. And then here you can see the finished prototype, which was open to the public to come and visit during the summer of last year. So it looks like quite an alien structure, the inflatable gold structure sitting on this simulated Martian landscape, then with the simulated underground accommodation actually in a converted shipping container underneath the inflatable structure. And people were able to come in, do workshops on how to grow plants hydroponically, how water recycling works, how to use old materials to make new things and so on, encouraging the idea of just living more efficiently, not only on Mars, but also on our own planet. And here you can see another close-up of the prototype. It was gold to reflect solar energy, so you don't get so much heat gain within the inflatable structure. And then with these louvers on to the glazing, again, to protect the structure from solar radiation. And then we worked with this graffiti artist who decorated the outside of the containers to give information about living on Mars. So it was a sort of information and educational, but also just an enjoyable structure for people to visit. And here you can see Andy Council, who is the artist. This is his work on the outside of the module. And here's some interiors. So these are the two artists, Ella and Nikki. This was their sleeping pods, where they would have slept, where they could work. They had a bathroom, you can just see through the door here, which would have used recycled water, and which was specially developed by the German company Duravit as a space toilet. It also had an aerated shower within there. All the air would, of course, be constantly purified and recirculated. And then we also worked with another artist, Katie O'Connor, who you see here, who developed a special hydroponics installation, which grew inside the prototype throughout the summer, had things like herbs and other plants that you could eat. Everything in there was things you could eat to help sustain the astronauts as they lived in this prototype house. And that, I think, brings me to the end of my talk. So I'll stop sharing there, and hopefully we can have some conversation about living in extreme environments. Okay, thanks, Sandra.
Thank you, Hugh. What a wonderful talk, as always. We have one question by Julian. Julian, you would like to please place the question yourself. I think that would be best. Okay, Julian has no microphone or camera. Then I will read the question from Julian. How would you keep the windows from freezing and bursting? And have you actually tried using inflatables as formwork for concrete on Earth?
So both really good questions there. To keep the water from freezing, you would have to have heat tracing in those windows to keep the water warm all the time, because I agree, otherwise if it freezes, it's going to break and burst the windows. When we made the prototype in Bristol, we didn't put water in there. So it's definitely still a sort of a theory or an idea rather than something that's proved in practice. And that's the same with using the inflatable structure as formwork, although other people have used inflatable structures as formwork in the past. So I would feel far more confident probably about that, perhaps, than even the idea of filling the windows with water. Although only, in fact, this week was I reading, I think it was an article in the German magazine Detail about using water as an insulant within windows. So this is definitely a technology which is new, but which I think we will see a lot more in the future. But yeah, good questions. Thank you.
Thank you. Nicholas?
Yes, I basically had the same question as Julian, but I was wondering why you wouldn't use like water on the inside, basically. Then you would completely avoid the issue of the water freezing, I would assume, or you don't have to need circulating water or heated water all the time, I guess.
Yes, that's a good idea. Maybe, yeah, put it on the inner layers, so you would have to either not heat it or heat it less. So yeah, that's an interesting concept. I think developing that window design in its own right would be a massive challenge, and yeah, it'd be interesting to it would be interesting to put more thought and effort into that. So yeah, that's a great idea. Thank you.
Vincent?
Was there any point when you were thinking about 3D printing the structure or anything else on site? Like, because the logistics is, they're like kind of crazy and I think very, very expensive. Or is there like no material which you can use?
No, the idea of 3D printing is an excellent idea. And whilst the concept would be that some of the accommodation would be under the surface of Mars in the lava tubes, you would still have to use probably 3D printers or excavators to form the accommodation within the lava tubes. So I think that would be, really an excellent opportunity for using 3D printing. We were also thinking that you could have used 3D printing to make some of the fixtures and fittings or furniture within the module itself as well. Things like the kitchen and so on, or other elements, could be 3D printed using some of the material on Mars. And in fact, 3D printing on Mars is entirely feasible because the surface is got this layer of dust, which is called regolith, and there's a lot of ice, which is possible to melt, and you can mix the two together and create a perfect medium for 3D printing. And there's no surprise that lots of the proposals, I guess, for building the first habitats on Mars do rely heavily on the concept of 3D printing for creating structures.
Thank you.
Have you experimented with 3D printing in the office?
Yeah, we use 3D printing quite a bit for testing sort of prototypes and even for model making. Yeah. It's really handy, particularly doing things quickly to test out three-dimensionally how they might work, test out joints between elements and so on. Yeah, we use it quite a bit.
But you have not applied it yet to an Antarctic station?
No, we haven't. I guess in Antarctica, it's potentially, I mean, 3D printers in Antarctica are already used to some degree in the science. And I think when we design for Antarctic research stations now, we allow more and more space for 3D printing, in particular for manufacturing spare parts for pieces of science equipment, which otherwise would have to be flown in and may delay an expedition going out into the field. And I think we're going to see more and more of that situation whereby maintenance is facilitated by 3D printing, but we haven't yet reached the stage where whole buildings in the Antarctic are made through 3D printing, but it'd be fascinating to see how that sort of develops over time.
May I ask one more question? Which materials have you used
for
the printing?
So, I mean, most of the time that we do our printing here, I actually can't remember the name of the material. It's that sort of little thin, you know, almost plasticated material.
Okay.
Yeah, it's not very nice. It smells really unpleasant. So we actually have the printer isn't in the main part of the office because, you know, we try to keep the smell and the fumes away from everybody when they're working. But I like the sound of it. It's so nice.
Ben, you had a question?
Yes, as you mentioned, you work with a color psychologist for the interiors. For my liking in the pictures I saw now, there's still a lot of dark blues, yeah, like colder colors. And also lighting is also really, yeah, almost like in a hospital, I'd say, in some places. What was the thought behind that, or why did you choose like, yeah, and still a lot of like colder colors in an environment that's already cold?
Yeah. So yes, good questions. So with the lighting, I mean, to some degree that depends on you know, when we're showing, you know, when the pictures were taken and so on. But all the lighting has a daylight simulation function attached to it. So it may be, you know, maybe brighter at certain points in the day, but it does drift off in the evenings and in the mornings. So it does ebb and flow a bit like daylight during the day. Obviously, there's a lot of different functions within these buildings. So you need the lighting levels to be quite high for certain functions, particularly in the kind of science areas. In terms of the colors, it's quite interesting within the difference between the two stations that I showed. So at Halley, the color psychologist chose two different groups of colors for between the stations. So for Halley, she used a color palette that she calls her spring palette, which is very, very vibrant, bright colors, which I guess in some places may have the effect of it almost seeming a bit cold, but the brightness was there to, in many ways, overcome the effect of the total darkness outside, rather than to make the place seem warmer. Whereas in the New Zealand base, you know, there are many more timber finishes. The colors are much more related to landscape. She calls that her autumn group of colors. And yeah, I like to think that that will be a much warmer kind of feel. So there's sort of differences between the two stations, but you know, you're aiming for a balance between daylight simulation, functionality, and then a degree of warmth in some places.
Okay, yeah, makes sense.
Thank you very much. Nicolas, you have a question?
Yes, I have another question. Do you have design principles that you developed or learned about that you think could be applicable in different parts of the world? Like, for example, we're thinking about Siberia and Mongolia with continental climate, or Hokkaido or something, where you think though some of the principles could be usable, or is it simply something for like these extreme cold climates like Antarctica and yeah, Mars and the Moon, for example?
Oh, no, absolutely. I think many of these principles would be very applicable in many other places on Earth. The idea of elevating the building above the ground, particularly in the Arctic, where you get permafrost, which then melts to a different level during the summer. And when you build on the building slab on the surface, you can get differential movement and cracking of the slab. So elevating the building on legs, which then goes deep down into the permafrost, keeps the level stable. Elevating the building also allows the air to flow underneath and therefore prevent snow drifting in winter round the building. So I think that's very applicable in the Arctic, and already a principle which is used in some Arctic buildings. The level of air tightness and insulation that we find in these buildings, I think also is particularly applicable to other cold regions, because it reduces the amount of energy usage that's needed. Equally, reducing water has application in both warm and cold places, because water is so expensive and difficult to produce. I mean, those are just a few of the examples, but I think it's probably no surprise that in researching the design of buildings in Antarctica, we actually went on visits to see buildings in the Arctic, to see how people have been building structures in northern Scandinavia and particularly in Alaska for decades and decades, to see what lessons we could learn and how we could apply those to Antarctic projects. And there are some things that are negative. In Alaska, of course, oil and gas are so cheap that the buildings are often not that well insulated, but they do have all sorts of issues with drifting snow that they've developed quite clever and sophisticated ideas for dealing with, that we've then reintegrated into our design. So there's a lot to be learned in both areas from the other area, I think. Yeah, and I think as the climate challenge increases and we get more areas that suffer from flooding, you know, some areas get warmer but suffer more flooding, some areas get colder as a result of climate change. You know, many of these principles from extreme environments will start trickling in and become more commonplace in more temperate environments. Temperate but more extreme environments.
Okay, thank you very much.
Cool.
Thank you very much, Nicholas. Do we have one more question?
Yes, I would have some questions about the aerogel. The first one would be, how thick are the aerogel windows you showed us on the picture?
I'm actually just looking around this room I'm in, because I know there's a piece of it. Hold on a minute, let me see. Can I?
That's cool.
I'm just gonna go and get it for you, and then I'm gonna show you.
Okay,
Hold
perfect.
on a minute.
Thank you.
I got it. It's here. This is just a sample, but you can see it's not very thick. It's like it's thicker than a normal double glazed unit. It's actually made by a German company called Ocalux. Oh yeah, there you go. Sorry. And you know, it's what is it? Maybe 2 or 3 centimeters thick. Not so thick, but it's full of aerogel, which is why it's solid white. It's 2 layers of glass just filled with the aerogel. But the U value of this glass is 0.6. So it's a lot better than a standard window, which would be like 1, I guess. I think at Halley we had a thicker unit, and we may have got down to 0.35 for the U value, which is almost like an insulated wall. So it's pretty efficient.
Do you know if the aerogel was on a silicate basis?
Yeah, I think so. Yeah. Yeah.
And what do you know about the light?
You can look it up. If you go on the Ocalux, OKALUX website, they have information about it there.
Yeah, thank you. Perfect. I already wrote it down.
All right,
and
great.
one more question about it. what do you know about the life cycle of the aerogel? Like, for example, how long can the window last and work efficiently?
I don't know, but there has been no degradation of those windows, and they've been there now for 9 years. So I don't think it's not like if you have a double glazed unit or a triple glazed unit and you put gas in it, then you can, over time the gas starts disappearing out of the cavity, and therefore the U value gets worse and worse. It's one of the problems with gas filled windows. But the aerogel isn't a gas. I mean, it is an actual material. So as long as the window is well sealed around the edges, and here you can see there's lots of silicon around the edges, then none of the aerogel will escape, and so the performance should last for much longer.
Yeah.
The one caveat is they're very expensive, these windows. I can't remember how much more expensive they are, but it is a lot more expensive.
Sure, but maybe that would change in the future.
Exactly. Yeah, as it gets used more often.
Yeah.
Yeah.
Yeah. Thank you very much.
Oh, great. Thank you. Oh, thanks, Sandra. You've put the link in the chat.
Yes, thank you. Any question?
I would have one more question about the Halley VI, the British Antarctic Research Station. This is built on skis, right? So
Yes.
I was wondering also, the buildings are in one line, and I was wondering, how did you fix the building so it won't go, won't
Yes.
break on the sides?
Yeah, very good question. And so what that was a concern at the early stage of the project, that the wasn't so much that the buildings would tip over, but that in the wind they might slide around a little bit relative to each other, and people could even suffer from a degree of motion sickness inside the buildings. So in the design, we have the ability to link the top of one corner with the bottom of another corner with cable to keep them more rigid. And also in each ski, there was a hole made in the middle so that you could put a steel plate through the hole, a bit like the centerboard on a sailing boat. And that would go into the ice and then lock the ski to the ice to prevent it from sliding. So that was designed and it was constructed like that. And the first season that the buildings were finished, they were on the ice. And then what they discovered is that the ski gets a little bit warm in the sun, and then the ice just melts a little bit underneath and then refreezes, and the ski just sticks solid to the ice. And it's so solidly stuck that it doesn't move. And the only way to move it is to hit it with a rubber hammer, and that sudden moment of friction breaks the bond with the ice. And in fact, if you ever see an aeroplane when it lands on the ice and then it's left overnight on the ice, in the morning when they try and take off and their propellers are going, they can't get the aeroplane to move because it's still stuck to the ice. So the pilot gets out and he hits the skis on the bottom of the aeroplane with the rubber hammer, breaks the bond, and the plane shoots off. And basically it's the same principle. We're using the sticking power of the ice to stick the ski to the ice, and it was unnecessary to do all the other measures that we'd included.
Okay, thanks.
This is fascinating. Thank you for the question, Karina. But how did you find out? You screwed it? So you used the screw and then found it out? Or you?
No. We found out that it stuck to the ice before we ever put the first steel plate in. And then everyone went, well, the steel plate isn't necessary. So they were never used.
Interesting. And this,
Yeah.
the steel cable, the cable for
No, they never used those either. The building was rigid enough that they discovered it was, all these things were excess structural engineering, I guess, not necessary. But sometimes the calculations can show one story and the practicality can show something slightly different. And we've even discovered this with our project for the New Zealand station. There's a big challenge with making the building in New Zealand and putting it on a ship and sailing it to Antarctica, because the sea is very rough and the waves can go up to sometimes 20 or 30 meters. But the shipping period, when we will do the shipping, the maximum wave height will be maybe 7 or 8 meters. But even at 7 or 8 meters, the ship goes along and it rises up the wave and then it accelerates down the wave again. And the accelerating motion of the ship down the wave can impose a massive force on a building structure, not something that building will ever experience on land. So we have had to design the structure to suit the shipping, even though it only lasts for 3 weeks. So there's much more structure in the building than is probably necessary even in Antarctica. But because this method of construction will save environmentally and financially so much, it's seen worthwhile in designing for that. But even in the design for that, we've done a lot of computer testing and physical testing. And the computer testing told us we needed way more screws and fixings than the physical testing, because I think sometimes the structural engineering programs, they just have such a big level of safety built into them that in reality, it's not always necessary. And that through physical testing, you sometimes find you can use much less material than you thought you would need through the computer testing programs. It's been a really interesting experience, that.
It's very interesting to deal with that also for current climate-related architectural challenges. For what case do you design the structure, right? Do you really design it for the few peaks?
Yeah.
Super.
That's a question we have been having about the cladding for the New Zealand station. Does it need to be watertight for the 1 in 500 year wind event? Or is it okay for just the 1 in 100 year event? In 1 in 500 years, that wind event will be so horrendous that rocks will be blowing around the site. It'll probably be necessary for everybody to be hiding in, almost one place. So if some windows break or some water gets in, that's probably not the main issue. The main issue is how do you get these people even out of Antarctica, because it's become so dangerous. So sometimes I think we just have to think through the problem. What is the main issue here? It's not, to prevent us doing excessive engineering. I think that's been an interesting question we've had to answer.
It's also a wonderful connection to general architecture, and also in that you can learn a lot from extreme architecture design for normal problems on Earth. It's another way of thinking, right?
Definitely. And that was the principle, really the most important principle around our project, the Mars prototype project. It wasn't to make a house which was totally suitable for Mars, because this is what NASA and ESA are struggling with, and it's going to cost billions of dollars to come up with the right solution. But our project only cost maybe 70 or 80,000, 60,000 euros maybe. It was and most of that was people giving their time and money for free. So in fact, it cost less than that. But the real interesting challenge of that project was think about Mars, and by thinking about Mars, how can we also think about Earth? If you go to Mars, you want to use less water, you want to use less space, you want to grow your own food. Well, wouldn't those all be good strategies for living more sustainably on Earth? If we all used less water, we lived in more ergonomic space, we grew our own food, we reused our clothes. All of these are simple measures which all of us can adopt to live more sustainably on Earth, to reduce our environmental footprint. And I guess that's what the project was really about.
I have one more question related to the water treatment. Maybe I missed it, but is water cleaned?
Yes. So in Antarctica, the water is made in a number of different ways. At Halley, the water is melted from the snow and ice, and then it goes through a filtration system through a series of membranes to make it suitable either for washing and cooking or for drinking. At Scott Base, the water is made through reverse osmosis by extracting water from the sea, and again going through a series of membranes to make it suitable either for cooking and washing, and also for drinking. So in every case, yeah, it goes through a filtration process. Now, for the idea for the Martian house was that instead of having any wastewater, you would just recycle the water again and again and again. But this is a big psychological challenge, and one that, for example, ESA operated a program at the French-Italian base Concordia, recycling black water. And although technically they were managing to achieve clean water from black water, people found it difficult to drink, knowing what it had been. It was like in their mind that this water had been full of shit, basically, and they didn't like the idea of drinking it, even though someone told them it's okay, it's clean now. So it's really interesting how we overcome the psychological challenges that we are able to technically manage, because the two are different things, technical and psychological challenge. And I think within space exploration and space design, more thought and effort needs to go into some of the psychological challenges. It's always interesting, I found, that when we have done small exercises we did one with NASA, looking at the minimum amount of space that people might happily live in. And the challenges were never around technical things, because the engineering is either there or it will be there. It was around the psychological side. And the reason they were interested in our experience was because of the ways that we had dealt with the psychological stress of extreme environments, color, lighting, materials, ergonomics, and so on. And I think that this is the great thing about space architecture, is that now more and more people are thinking about the challenge for people of extreme environments, not just the engineering challenge of extreme environments. We need to think about both, but we definitely need to think a lot about the human factors. And I think, Sandra, if you think about some of the conferences we have been to, when we first started going, it was a lot about people talking about, I don't know, gravity or the cool machines that you could invent. And now there's a lot more thought around, lighting and ergonomics and spatial relationships and so on. I think, it's developed a lot over the last 10 or 15 years, that whole conversation.
It has also opened up a lot to a lot of more professionals.
Yes.
More artists, more sociologists, psychologists.
Yes.
Landscape designers. Yeah, lots of ideas.
Yeah.
Okay, do we have more questions from the students? Otherwise, I was surprised of you showed the images, the Discovery Hut from 1902 or 1905, Robert Falcon Scott Discovery Hut.
Mm.
And it's an actual photo, right? An actual image. But was it rebuilt? Was it preserved? How can it look like this now?
It's a little bit of a trick because the buildings have been preserved very well because the environment in Antarctica is very dry. So if we think about it, most buildings, the worst thing for buildings is water. Whether rain, moisture, and then freezing of water, and then melting of water. These are the things that cause the most damage to buildings. And in Antarctica, it's so cold that all the water gets frozen out of the air. So it's actually very dry. So there's no rain and there's very little moisture in the air. So this does help to preserve things for really a very long time. And it's amazing that within these buildings, they found tins of food with the label still intact and the food still intact inside the tins. So it's amazing. However, some degradation, some problems did arise with these buildings, but they are now looked after by heritage bodies. So the 3 buildings, is there 3? 4 buildings on Ross Island, the one at Scott Base, the Discovery Hut, and then Captain Scott's Terra Nova Hut, Shackleton's hut, and Borchgravink's hut. So there's actually 5 on Ross Island. They're all looked after by the New Zealand Antarctic Heritage Trust, and they have done big projects of restoration to improve their performance whilst maintaining them in their original appearance. So the weather has helped, but some human intervention has also helped with the preservation.
Thank you. Then I have one more question. If there are no other questions from the students, if there are, please interrupt me, because we have only a few minutes left. The topic of how to design for people that you don't know, for an environment that is not known in an extent that it's so easy, you have to prefabricate everything, is super exciting for an architect. And what you said, that you design some parts and then you use them, or you change the idea, the concept. Similar happened to the Skylab station when it was the first station for people living in microgravity. There were a lot of design features that were not used, and some that were very related to human psychology. So is there any other part except the one for the legs that were used differently?
Oh, absolutely. So what's really interesting is that's such a good point, because in all the projects, we do so much consultation with people who have lived in these stations in the past. But very often they won't go back to Antarctica again. So you rely on their experience, but they won't necessarily experience the thing you have designed. So, I mean, we are about to do this whole process. We're about to start it all over again with one of the Australian stations, where we will meet with people who've lived at Casey Station, people who have done science there, people who do the logistics, and we will be asking them, what works well, what doesn't work well, etc., etc. But we won't come up with the same solution that they had in the past. We will be listening to their ideas and coming up with new solutions, and then completely new people will move into those buildings and use them, and they will develop their own experiences, which they will give to the next designers who redesign the buildings. So it's really interesting the way you're always relying on past experience for future construction, and the people who give you the experience don't necessarily move into the building. It's a bit like asking astronauts who've been to the moon or been to the space station about their experience. But the reality is that those astronauts will probably never go back to the space station again. And instead, new astronauts will go there, from a different generation or a different age group with different requirements. And yet you designed it around the past people. It's just, I don't know how you overcome that. But the key is to build in as much flexibility as possible to allow the people who come in the future to easily change, in particular, the interiors of these structures. So one of the things we have learned is that we find a grid for the structure, often around 6 meters, and we use that everywhere, so that bedrooms are designed around a 6 meter grid, laboratories are designed around a 6 meter grid, vehicle workshops around the 6 meter grid, so that in the future, the interiors can be stripped out and changed to meet the requirements of which we have no idea even at the moment. Imagine we're designing an Antarctic station in 2023, which will still be operational in 2080. How can we know what the science and the technology is? So the answer is be generous with the space, use the same structural solution everywhere, and have the minimum amount of structure in the interior environment to allow for the space to be changed to suit future requirements. And we already see this in Halley. A room designed as a gym is used 1 year as a gym because the crew are really interested in fitness, and the next year they use it as a music room because they do their fitness by skiing outside, and they're more interested in making music when they're inside. And the same with laboratories. We have a laboratory that's used for analyzing the clean air 1 year, and it's going to be used for glaciology the next year, and the requirements are slightly different. So I think that being easily able to access the services to maintain them, and easily flexible so you can change everything, are kind of really key drivers. We kind of start with that. We agree with that as a principle. We start with that, and then we design always knowing that we've got to have that as a characteristic of the building.
Yes, that's wonderful. The possibilities. It's all about possibilities, right?
Absolutely. Not preventing future possibility or opportunity.
Which is also fits to the of the sustainability definition from the Brundtland report. No.
Exactly.
Not prevent future uses.
Yes, exactly. Because one of the best ways to be sustainable is to reuse what you've got. So exciting and nice as it is to build Antarctic research stations, I just hope that they all last for a long time and can be reused by future generations to do things that we can't even imagine.
That is wonderful, that architects have to think now. This is another lesson learned for Earth architecture, right? Think of the material within a life cycle.
Yeah.
So not just for the use of the first people, and then I have a last question, please.
Oh, can I just say one more thing about that? Because I think that is one of the amazing potentials of technology as well in building design. So now within the digital information, we talk a lot about the idea of a digital twin, basically making your building physical, but also making the physical building fully represented digitally, and including information about all the components and materials that are in the building, so that when eventually you take the building apart, you know that the beam is a piece of steel that weighs this amount, that it was made in this place, that it's this percentage of carbon and this percentage of iron ore and whatever, and it has this load bearing capacity. So then you can reuse it because you have all the information necessary about it. And I think this is a really exciting potential for building information modeling, is to give as much information about all the materials and the products in there to enable their reuse in the future. And that's also an important part of the sustainability.
I would have a question regarding that. So when you said that you're going to build a new base and that hopefully it's going to last until 2080, did you already come or think about a solution how to overcome the raising ocean levels, and will those new bases be able to float, or
Yeah, well, to be honest, the easy way that we address that problem is that we work with climate scientists who help us to predict potential sea level rise around these sites. And then as a general rule, we site the buildings outside the zone of the sea level rise. But it is an important point because many of them are very close to the sea, because that makes it easy to deliver the materials and to resupply. So we, for example, for the New Zealand base, we worked with the New Zealand National Climate Research Organization called NIWA, and they helped us to predict sea level rise, but also the impact of tsunami if it develops in the Pacific Ocean and came towards Antarctica. And then we set the building above the predicted tsunami line to make sure that it wouldn't be affected by that. When we built the British Antarctic station, the buildings are much smaller and they're all made of glass fiber. So there were some companies who proposed floating the buildings to Antarctica, but in the end they weren't made in that way. But it would be another way that would potentially, these buildings could be constructed that would be efficient, would be to make them so they could be floated. But we haven't done that. But it's a really interesting idea.
I think it has a lot of potential for a research project or academic project.
Yeah, definitely. I mean, we have thought about buildings as as a train. So the concept from Halley of modules that are connected together, we're using that again for one of the Australian projects, which is for a camp to support one of their aerodromes, which has got fewer modules. It actually only have 5, and the modules will be smaller, and they will all be connected together in a line because the wind only blows from one direction. But they will be, you will be able to put steel bars between the legs, so that they literally are connected together like a train. And then as the snowdrift comes closer to the building, we will connect them up and then drag them 200 or 300 meters, and then the snowdrift will build up again, and then we'll drag them back to where they were, having flattened the snowdrift. So they'll go backwards and forwards like a train. So it's interesting. I mean, we talk about buildings being floated, buildings being pulled like a train. We use components from the transport sector, like the connectors between train carriages or skis from sledges. I think within these extreme environments, there's so much to be learnt from other industries, but also other cultures. I remember watching one of those amazing I think it was a David Attenborough program about people living in cold regions and seeing nomadic people in Siberia who actually built their camps as sledges that they then move from place to place to suit the hunting requirement or suit the weather and so on. And there is a lot to be learnt from traditional culture and from other industries other than architecture. So please don't always look at, you know, the architecture websites for the best ideas. That's one place, but there's a lot of other really interesting places we can learn from. Ships, trains, planes, traditional cultures, all really good sources of information.
That is actually a wonderful conclusion to your talk and fits very well to the topics of the module. Shall we do? Yes. Or is there any last question? Otherwise, I would like to thank Hugh Broughton very much for his talk and insights into a world that we don't know, and that's super exciting. Thank you for taking your time, and also thank you to you students for the interesting questions.
Yeah, thank you so much. It's lovely hearing the questions, and there's all really good, brilliant questions. And I'm also excited as well that you are studying this module, because you'll learn so much from this module, not only to apply to extreme environments, but as we've discussed today, to projects, could be even in the center of Vienna, but there are definitely things to be learned from extreme environments, which will be beneficial for everybody anywhere.
Thank you very much.
Thank you.
Thank you.